Okay, last section of chapter 7, improper integrals. Okay, for the definite integral f of x dx from a to b, so far we assumed that the length of the integration interval ab is finite, and that the range of the integrand f of x remains finite on this finite interval. However, we may be curious what happens if either one or both of these assumptions is not satisfied. Okay. If either or both the limit of integration becomes infinite, or if the function f of x becomes infinite somewhere in the interval ab, then the symbol integral a to b f of x dx is called an improper integral. It's not a proper integral. So it's improper integral. Here is type 1. Improper integral with the infinite interval, like this. Integrate this function from 1 to infinity, like this. Integral of 1 over x cube from 1 to t. Okay, then a of t. If we integrate it from 1 to t, then a of t can be obtained in this way. This shaded area like this. Then, if we send t to infinity, then limit a of t, when t goes to infinity, we can have 1/2 as it. So, the area of S, which is under the whole area under this function above the x-axis, it can be written in this way: integral 1 over x cube dx from 1 to infinity can be written in this way, and this value is 1/2. So we define the area of this kind of integral as this. Okay, this approach can be applied for like this, as you see in definition 1. Okay, type 1 of the improper integrals. The symbol, this is defined by the equation like this, like this, like what you saw just before. And symbol, this, is defined by the equation of like this. Okay. Okay. So find the integral from t of f of x from t to b first, and send t to minus infinity. Okay, then the improper integral, these are called is convergent if the corresponding limit exists. Otherwise, they are called divergent. So this value can converge or diverge. If both are convergent, then we can define integral minus of f of x from minus infinity to infinity, because each of these does exist. So the addition does exist. So those addition can be written as a integral of f of x on the whole real line. Okay. So first example asking us whether the integral of sine x from 0 to infinity convergent or not. As you see, from 0 to infinity, so we find the integral of f of x as a integral of sine of x from 0 to t first, which is this. And then send t goes to infinity. Okay, the graph of this 1 minus cosine t can be written in this way, and it diverges. So improper integral, this is divergent since the limit does not exist. The limit vibrates, so the limit does not exist. So it diverges. So the whole integral also diverges. This limit does not converge, so this integral diverges. This one. So we find the integral of x times e to the minus x squared from t to minus infinity, which is this. and then send t goes to infinity. So we have minus 1 over 2e, which as the value of the integral of the left-hand side. For this one, we find, we just divide this integral to two pieces and check find one integral from 0 to t and another integral from t to 0. And each of integral ended as a 1, so the whole integral can be written as 2, like this. Determine the value of p for which the integral 1 over x to p dx from 1 to infinity is convergent. For this one, we have to classify the cases when p is equal to 1 and p is not 1. So we divide it as two cases first. If n is equal to 1, this integral can be easily found as the infinity. When p is not equal to 1, then we have to think then we first integrate this function from 1 to t, which give us this. In order to analyze the limit of this function, so we have to separate the case as p bigger than 1 and p less than 1. When p is bigger than 1, this t to the 1 minus p goes to 0, which gives us the integral as 1 over p minus 1. But if p is less than 1, then t to the 1 minus p diverges, which therefore the integral from 1 to infinity over 1 over x to p dx is infinity. So here diverges and here diverges, and it converges only when this is true. So if p is bigger than 1, it converges. But if p is less than or equal to 1, it diverges. And this is the answer. And this is the interval that was asked to be found. Okay? As you see, this is a very important example. From 1 to infinity, the integral of 1 over x square, integral of 1 over x square from 1 to infinity converges. But integral of 1 over x from 1 to infinity diverges. This is a very important example. Okay, this fact will be used for comparison test. Okay, next. Type 2, improper integral for which the integrand become infinite. This is this case. This graph goes like this. So when x goes to 0, the function goes to infinity. Okay? Like this. So in this case, the definition for the improper integral of this type can be defined in this way. If f of x becomes infinite at x is equal to b, then we define integral a to b f of x dx as this. From integral from a to t f of x dx, but t approaches to b from the negative direction. Okay. If f of x become infinite at x is equal to a, then as you see in figure 4 here, like this. Figure 4, like this, you say here is from the left side, here from the right side. Okay, here find the integral from a to b f of x dx, then send t goes to a plus here. So here this can be written as a limit t goes to a from the positive direction from t to b f of x dx. T to b. The improper integral f of x from a to b is called convergent if the corresponding limit exists, and divergent if the limit does not exist. If f of x becomes infinite for some value of x is equal to c in a and b, both this and this convergent, then we define this integral as sum of these two, which can be written as sum of these two limits. Okay? Here, the right limit and left limit. And here, both limit converge, then we can write it. So example 5, asking us to evaluate integral of integrate x over square root of x minus 1 from 1 to 2. Here f of x is like this, and it's if we draw the graph from on the Sage cell, then we can easily find the vertical asymptote line and x is equal to 1. Because when x is equal to 1, the denominator is equal to 0. So this is a vertical asymptote, as you see. You can easily see from the graph. Then, by using the definition, then this integral can be written as like this, from the integral from t to 2, when t approaches to 1 from the positive direction. We can easily find the integral of that. So then we just take a limiting process to get 8 over 3, like this. We can also to use the Sage integral command on these two. Sometimes it works. If it does not work, then you can use this limit process. Okay. So you can if you so these are the cases that you may face when you use CAST tool, that the CAST tool does not give you the answer. So in that case, you can draw the graph first, and then if you find this vertical asymptote line or horizontal asymptotic line, then you can take the integral and limiting process like this, and then divide the problem to two pieces. Then you will be able to use the same tool to get the answer that you want to have. Is this integral converge or diverge? Okay, here. Okay. This is since when x goes to 2, then this goes to 0, so this value goes to infinity. So this given integral is an improper integral. But if you break it to the integral from 0 to t and take the left limit, then you will be able to find the integral value as pi over 2. So we can say the given integral is convergent. So for this one, we do separate, since there is a vertical asymptote line and x is equal to 1. So you separate it from 0 to 1, from 0 to 1 and from 1 to 3. Since there is a vertical asymptote line at 1, so you break it from 0 to t and send t to from the left hand side. Take a limit from 1 to from the left hand side and break it from 0 to t s to 3 integration and send s to 1 from the positive direction. And then you're going to have the limit on both sides as 3 and 3 times cube root of 2. So the integral value of this one does exist, and 3 plus 3 times cube root of 2. Next, this one here also you will see this at x is equal to 0, it has minus infinity value, so it has a vertical asymptote line, so it's an improper integral. So we break it to the integral from t to 1 and send t to 0 from the positive direction. Then this first part can be obtained by integration by parts, and then we can take the limit process to have 2 as the value. Here is the comparison test for improper integral. So when when we like to check whether the given improper integral converges or diverges, these comparison theorems can be used. Assume that f and g are continuous functions with this condition. Then if this converges, then that converges. If this diverges, then that diverges. Which means the smaller, the bigger one converges, then smaller one converges. But if smaller one diverges, then the larger one should diverge. Okay, it does make sense, as you see in this graph. Okay, prove. This one is convergent. As you see, this can be found like this, and you see this converges, so this converges. As you see, because 1 over x square root x converges. Okay, there are. I told you integral of 1 over x square, and the case of 1 over x square and 1 over x, and the same thing can be used here to analyze it. Here, okay, as you see in here, we checked the case, the convergent and divergent case for 1 over x and 1 over x square. And here, as you see, integral from 1 to infinity 1 over square root x dx is divergent. This diverges, that fact can be applied to analyze this case. So, by comparison test, the second integral that we have is this. So, from this condition, once again, the comparison test is the result, since this is convergent, so the smaller one is also convergent. Okay? Those things can be analyzed with the CAST tool too, with the CAST tool too. The last example is the CAST example. Determine whether the integral is convergent or divergent. Evaluate the integral if it is convergent. For this one, we just integrate from here, So, for this integration, we first draw the graph of it from -5 to 0. So, as you see, there is the asymptote here, and then we do integrate the function f with respect to x from -infinity to 0, as we asked. That gives us the answer like this. What this means is this Sage tools does work not only for the definite integral, but also work for the improper integrals without any further work. So use those tools when it works for the problem, exercise problems which was given. Okay? I think that will do for chapter 7. I think that's the end of chapter 7. This Hu Logong is one of the most respected mathematician in China. He was died just after this talk with heart attack in 1985 at Tokyo University. Okay, I think that's the end of this class.